first? Anybody have any questions about problems or anything? I was thinking we could wait to talk about the test until I get it back to you. All right, well, the next topic, we're still going to be using Newton's second law, but we're going to talk about circular motion. And a lot of what we need to do circular motion is stuff we already know about. We're going to have some new terminology, but it's the same ideas we've been dealing with mostly in lab for a long time. So you think about an object moving in a circle. Let's say the object's right here. And let's say it's going counterclockwise. We already know that the velocity vector is tangent to the path. We already know that the parallel part of the acceleration is in the same direction as the velocity if it's speeding up, and the opposite direction if it's slowing down. So this would be what it looks like if the thing was slowing down at this instant. And the perpendicular part of the acceleration is towards the center. And then the total acceleration is just equal to the parallel part plus the perpendicular part. And so I did all this, none of this was new. But there are a few new things that that's going to go into this. So here's the new stuff. And I'm just going to list it all out here, and then we'll just work on some problems and stuff. But it's a very small list of things that are new to us. The first one is for circular motion. A parallel is called I'll say A tan, and this is called the tangential acceleration. I didn't expect that to get such a good response. But okay, so here's where that comes from. We know that always, if you draw the path, the velocity has to be tangent to the path. We know A parallel has to be parallel to the velocity. So, we might as well say that A parallel is tangent to the path. That also has to be true. And so that's where tangential comes from. It's tangent to the path, tangent to the circle at whatever point it's on. Okay, so the first new thing is that we have a new name for A parallel. That's a pretty minor hurdle to overcome, And then the second one is A perpendicular. It's called, you're going to like this one too. Maybe not. Centripetal acceleration. So I'm going to write that as ACEN. Centripetal acceleration. And where that name comes from is centripetal just means towards the center. So if the thing's moving around a circle, then the part of the acceleration perpendicular to the tangent always points right towards the center. But again, that just comes down to like a new name for stuff that we've been using. And then there's one more thing. This is the only like mathematical thing. And that is the magnitude of a centripetal. I'll call it just the scalar a centripetal, is equal to the speed of the object squared divided by the radius of the circle. So this v is the speed of the object. This r is the radius of the circular path. And that's it. It's all the new stuff in circular motion. We are going to break it up into two different types of circular motion. But it's all based on this idea. Okay, that's it. The total acceleration, we've been saying the total acceleration is a parallel plus a perpendicular. Now for circular motion, we're going to say the total acceleration is equal to the a centripetal plus the a tangential. A centripetal is always present. You can think of that as the acceleration that's required to make something move in a circle. Because that's the one that makes it turn. And circular motion always has to have this specific type of turning. A tangential is only present if the speed's changing. If an object follows a circular path, moves in a circle, with a constant speed, then that's called uniform acceleration. And then the total acceleration is just equal to the centripetal part. There's no tangential part. If it moves in a circle with changing speed, it's called non-uniform acceleration. And then you do have a tangential acceleration. So the total acceleration, you have to add both of these. Anybody have any questions? Okay, so now I'm going to give you sort of a general set of steps for doing circular motion problems.
Like, yeah, like what if you were like, can you scroll down? I can't stand to look at your writing for one more second. Okay, so a general set of steps for circular motion problems. Except tetherball problems. So tetherball problems, that's just what I'm going to call them. And it applies to tetherball, but it also applies to other things that are similar to it. But we'll talk about that in a second. You can use this approach, but it's not the quickest way. So I'm just going to give you a slightly simpler approach for those. Okay, so the first thing you want to do is you want to choose a view of the motion. So something's moving in a circle. Okay, so can you visualize the circle that I'm doing right here? So you need to put your coordinate system in a plane where that circle is visible. Okay, so if the circular motion is like this, okay, your coordinate system needs to be like this, not like this or this. Okay, you want to choose a view, a way to visualize this motion where the motion looks like a circle, not where you're looking at it from, like a pizza slicer coming towards you. You know what I mean? You know what a pizza slicer is? Okay. So the first step is choose a view where the circular path is visible as a circle. So, like, for example, if you're doing a problem where, here's a toy train going around the little train set. Okay. The view you want would be like looking down from above or looking up from below. So you want to choose, let's say, a top view where the motion looks like that. And we'll put the coordinate system there. This would be the train. Okay. And then the second step, choose the point on the path that you're going to analyze. Sometimes a location on the path will be given in the problem and you don't have a choice. And sometimes you can just choose any one that you want. You'll just be asked a general question about how fast does this thing have to be moving or something like that. And then you can choose any point you want. So for example, in this train problem, let's say we decide we want to analyze what's happening with the train right there. You have to be specific about one point. Third, draw a vector from the chosen points toward the center. The center of the circle. This is the direction of the centripetal acceleration. That's the direction of a centripetal. And it has a magnitude of the speed squared divided by r. So in our example, there's the path, there's the location that we're looking at, there's the coordinate system, and this is the direction of the centripetal acceleration. So then the centripetal acceleration is a vector in this case. Is that pointing in the positive or negative x direction? Negative. This would be, you could think of it as negative v squared over r for the x component, 0 for the y component. If you ever get to choose, by the way, so on problems where you get to choose what point on the path you're looking at, you might as well always choose one of these 4 quadrant points. You could choose this point here, but then you have to use cosine and sine to represent the direction, and sort of unnecessarily complicated. So you might as well just choose, this, or this. For if it's non-uniform circular motion, calculate the tangential acceleration based on whether the object's speeding up or slowing down at that instant. Then, the total acceleration is equal to the centripetal acceleration plus the tangential. If there's no change in speed, if the thing has a constant speed, then a tangential is 0, and you only have to worry about the 1. Then sixth, so now we know as much as we can about the acceleration of the object. Now we want to use Newton's second law. So the first thing is draw a free body diagram of the object. You need that anytime you use Newton's second law, and then use Newton's second law. One thing that we haven't seen before, so one thing to notice is now for the first time, we'll sometimes have forces like normal forces and weight forces that are not in the plane of our coordinate system. And I'll give you an example. But sometimes weight, and normal force will be out of the plane of our chosen coordinate system. If that's the case, you can just leave them out. Leave them out of the free body diagram, leave them out of the Newton's second law, okay? So, for example, let's go back to that train example. The train track. If you draw a free body diagram of a top view of the train, what direction would the weight force be going? Yeah, straight into the picture, straight into the page. And what direction would the normal force be? Yep. So the normal force is out of the page. And so the only force you have is, well, it depends how you're doing this problem, but you'd have a force pushing this way that's like a force the tracks are applying to it. The weight force and the normal force wouldn't be there. Sometimes you do. It just is a matter of, so it depends which way the circle is going. So if something's in a circular motion like this, then your coordinate system is going to be like that, okay? And then when the object's over here, the weight force is in the plane of that coordinate system, so you do have to put it in, okay? Well, actually, I can make it simpler than that. Sometimes, I can tell you exactly when this sometimes is. So this sometimes is when you're doing a top-down or a bottom-up view. Okay, so if your coordinate system is horizontal, then the weight force is going to be out of the plane. And the question is, like, if this is your coordinate system, how, like, and your weight force is like this, how far do you go in the x direction and the y direction to get something going straight in? It doesn't make any sense, you know. There's no answer to adding up a vector this way and a vector this way to go into the page, so you just leave it out. It won't come up in the calculation. Okay, let's do an example. So let's say we have a fighter jet. I don't know what they look like, but I have seen Top Gun. This looks more like one of those like single engine planes that someone's grandpa in Northfield owns, or some kind of sea creature. Yeah, what? Why does that look so bad? No. Yeah, it does. It looks like a fish. What? Okay. Something about it looks wrong to me. Okay, and it's going in a circular path. And this is not drawn to scale. But let's say that the radius of the circle is 250 meters. That would make that plane like 300 meters long. They don't make planes like that. And let's say that the speed is 120 meters per second as it goes through this motion. And so let's say that at this point here, that's supposed to be exactly straight across from the center of the circle. So I'll call this point P. So A, at the point P, what's the acceleration of the pilot? And second, we're going to assume that the pilot's chair applies a force vector to the pilot with an unknown direction. And we want to know what is that force vector. And then of the three, this is the easiest one. Once we calculate that, let's say we want to know what's the force vector applied to the chair by the pilot. And this actually is a very realistic engineering problem, kind of thing that they do a million similar calculations when they're putting components in a plane or in any kind of vehicle. If you know what kind of maneuvers the thing is going to go through, you do these kind of calculations to figure out how strong the chair needs to be in all these different directions, like you have, it's connected to the floor by bolts or whatever, like how big do those bolts have to be? And this is the kind of calculation you do. You might be like, God, we could save some money if we went wicker with this chair. Let's see if we could, let's see if that'll work, or maybe we need to upgrade to like ABS or something, So, okay. So what's the first step? No, that's the sixth step. You've missed 5 steps. Okay, so yeah, we want to choose the view that where this circular motion looks like a circle. So that's actually pretty much the view I drew this picture in. I guess instead of, I'm going to do a lot of these on the same picture, so I won't write down those numbers. But okay, so there's the path. And we've already been told we have to analyze this point. So there's the plane on the way up. That's the, it's going this way around the circle. And the coordinate system will be like this. All right, so we chose a view with the coordinate system. We chose the point that we're looking at. That was chosen for us. What's the next step? So yeah, now we draw the centripetal acceleration vector. Oh, and I didn't say this really explicitly, but the idea here is that it's a constant speed of 120 meters per second. So that'll come up in a second. All right, so this is the direction of the centripetal acceleration vector. The magnitude of that is v squared over r. Case v is 120 meters per second, so 120 squared divided by 250. Or 57.6 meters per second squared. So yeah, I haven't done it as a vector yet. I just first got the magnitude, but yes, it's in the negative x direction. So as a vector, the centripetal acceleration is negative 57.60. And, excuse me, depending on what point you are solving for, you know, this has the same speed everywhere. So you'd have the same magnitude no matter where on this circle you were looking at it. But you'd have different directions for that centripetal acceleration. If the plane was over here, that would be positive. If the plane was down here, that would be positive y. If the plane was up here, that would be negative y. All right, so this is constant speed. And so this is uniform circular motion. And so that tells us that there's no tangential acceleration, what we used to call the parallel part of the acceleration. So the total acceleration vector is just the centripetal acceleration, so it's negative 57.60. Any questions about any part of that calculation of acceleration? All right, so this wasn't asked in the problem, but if you're going to design a plane, this is maybe one of the things you might want to think about, like, is this pilot still alive? Anybody have a sense of that? Like as you accelerate, your brain sort of gets centrifuged and stuff. Like, is that an acceleration people can survive? Well, it's about right around 6 Gs of acceleration. And so, yeah, that's a pretty major acceleration, but for a small amount of time, you can be all right. If that went on for very long, you would pass out. And if you're the person flying a plane, you don't want to pass out. I don't know as much about planes as I sound, but that's pretty common sense, Everything I know about surviving accelerations in planes comes from like a 10-minute chunk of a show on Nova that I saw once. Okay, so this is part A. So now we know the acceleration of the pilot. Oh, and I didn't give the pilot's mass. Pretend I did. Okay, what's the force vector? Let's say the pilot has a mass of 100 kilograms. That just makes it nice and easy. Okay, so if we want to calculate the force applied to the pilot by the chair, what's the next step? Yep. So now, free body diagram of the pilot. How do we know to isolate the pilot? How do we know not to isolate the chair? That might be reasonable too, you know? You know, really, this sounds like a joke, but this really is kind of the truth. Like, whenever you're doing a problem that's been made up by someone else, like this wouldn't work so much if you're an engineer because you can measure the masses of whatever. But if you're doing a problem in a test that somebody else has given to you, you probably want to isolate the thing that they give you the mass of, you know, because the weight is going to probably have to appear in the free body diagram in the equations. And so, yeah, you could isolate the chair and do the same thing if you knew the mass of the chair, but we don't have it, you know. Okay, so at this point in the circle, the pilot, you know, the plane's going up, so the pilot's sort of facing straight up. So that's why my free body diagram is going to look like this. So here's the pilot. And what forces are acting? So yeah, so gravity always acts, but now in this chapter, it doesn't always show up in the free body diagram. Does it in this case? Yes. So the weight is going to go just like this, and that's because we're not taking a top-down view of this motion. We're taking a side view. Anyone have any questions about that? Okay, so the mass is 100 times 9, no, the weight is 100 times 9.81, so 981. And now you go around the boundary of the chosen object, looking for places where there's contact with the surroundings. Where is there contact? The chair, and that's all. Okay, like the back of the chair and the bottom of the chair, but we're just going to call it all one unknown force vector. So, question? Let's pretend he's too short for that. Or let's pretend the chair has footrests, and that's part of the force we're calculating. So usually, always up until now, and I mean, pretty much it's going to continue to be this way. We've known the direction of the forces. This problem says we don't know the direction, so we're just going to say there's some unknown x component of the force and some unknown y component of the force, and we want to calculate both of them. So Newton's second law says 0, negative 981 plus, I'll just write this as fx and fy. You can put them in separate vectors or the same vector. And that's equal to mass times the acceleration of the chosen object, which we already calculated, negative 57.60. And so the x equation says fx is equal to negative 5,760 newtons. And the y equation says negative 981 plus fy is equal to 0. So you can solve this, and it says Fy is equal to positive 981. And so that total force vector, that's the force on the pilot by the chair, is equal to negative 5760, positive 981. Or in other words, if you want to visualize the direction of this, if this is our coordinate system, we have a big negative x component and then a small positive y component. So the head of this vector would be somewhere like this. It has to be in the second quadrant with a positive, with a negative x component and a positive y component. And then the last step is, now we want to know, for part C, what's the force on the chair by the pilot. How are we going to do that? Yeah, that's just Newton's third law. So we just multiply the previous vector by -1. And so we get positive 5760, negative 981, or the exact opposite direction of this. So somewhere like that in the fourth quadrant. And so would the pilot here feel like he's coming off his seat, or would he feel like he's being mashed? Mashed. So if you, the chair's pushing into his butt, you know, or in other words, he's pushing down on the chair, so it feels like he's being compressed. Yeah. And so now the engineers look at this and they test out their different chairs and they're like, okay, yeah, Wicker's fine. Any questions about that problem? Let's do another one. So let's say there's like a smooth surface, like you can imagine a glass table or something. And there's a stick in the middle with a string attached to it. And a ball is attached to the string, spinning around this circle. So this is a glass surface. It's not, the idea is this isn't like a tetherball game where all you have is the ball hanging by a string. It's also being supported by the ground underneath it. Okay, and that lets this string be horizontal. And let's say that the radius of this circle is 0.25 meters. The mass of the ball is 0.06 kilograms. That's 60 grams. That's about the weight of like a pinball. And let's say that it's moving around the circle with a constant speed of 6 meters per second. And we want to know what's the tension in the string. So the first thing we have to do is choose a view where that circle is visible. So I'll do a top-down view. And that's going to be the coordinate system. And then it doesn't say anything in this problem about what point we're looking at. So that means we get to choose. I'll choose a different one just so you can sort of see how it all works, but I'll still choose one of those 4 easiest points. So this is the point that I'm going to look at. And from a top-down view, it's going this way. That's the direction of the motion around that path. And so now draw the centripetal acceleration vector. So that's from the point you're looking at toward the center. And the magnitude of that is the speed squared over r. We're given both of those again. So that's 6 squared divided by 0.25. So 36 times 4 is 144. And now we have to put that into vector components. That's pointing in the positive y direction. So the vector components are 0, positive 144. It's uniform circular motion. Yep. So uniform circular motion, bless you, says that the total acceleration is just equal to the centripetal acceleration. So the total acceleration is also 0, 144. Okay, so now we know everything about the total acceleration vector. Now we want to do a free body diagram of the object because we're heading towards Newton's second law, so we can calculate this force. So the object's there. Forces are acting. Weight is always acting, but what direction is it in this problem? Yeah, in this case, it's straight into the board, into the page, and so we can just leave it off. Okay. What about the normal force? Same thing, that's coming straight out of the page, so we'll leave that off. And is there anywhere else around the boundary where the surroundings make contact with this object? The string, yeah. And so at this point, at the bottom of that circular motion, the string is this direction. And so the pulling force has to be away from the chosen body toward the string, so it has to be up. And so that's a complete free body diagram. You actually, if you want to represent three-dimensional things in a two-dimensional picture, the way people do that is you draw, so if a vector is coming towards you, you draw it like it's the point of an arrow. And if it's going away from you, you draw it like it's the feathers of an arrow. So you do it like this. The weight is going away from the viewer here. So you would write that like this with the weight. And the normal force is coming towards us. So you'd write that like this. But you can just leave it off too. You see how that's supposed to be like a sort of a point coming towards you, and this is supposed to be the feathers of an arrow going away from you. Either way, those aren't going to show up in our Newton's laws because they're not in the plane of our axes. So Newton's second law says, well, take all the forces. The only force that shows up here is the tension in the positive y direction. So I'll write that as 0t. And that's equal to the mass, 0.06, times the acceleration, which is 0.144. And the x equation then says 0 equals 0. The y equation says t is equal to 0.06 times 144. And that comes out to 8.64 newtons. So if you set up this problem, set up this system, this thing's spinning around on the table, and it's being turned in that circular motion by this string. The string has to be strong enough to support a force of 8.64 newtons. Yep. No, you'd be able to. So let's see how that works. Okay, let's just do it again. Like, what if I'd chosen a different point? Okay. So there's your coordinate system. And let's say now we're going to choose this point. Okay. That's the direction of the centripetal acceleration. The magnitude is the same as it was before. 6 squared over 0.25. So 144. And now put that in a vector. This is, before it was in the positive y direction, now that's in the positive x direction. So 144, 0. And that's our total acceleration because it's uniform circular motion. Yeah, exactly. Right. So the tension changes too. So free body diagram. So now the only force that's going to show up is the tension this way. And so Newton's second law says T0 is equal to 0.06 times the vector 144, 0, And again, you get T is equal to 8.64. And it would work the same if you put them in either of the other two simple locations, because then you just have negatives everywhere. They'd cancel out and you'd still get this value of 8.64. But if you ever do have a problem where, that does come up sometimes, you do these things and you have an acceleration in one direction and you don't have any forces in that direction, it means your free body diagram isn't right, So, so that is something like, if you come up with a Newton's second law that's impossible, you just chose your forces. There's a force somewhere that you didn't think of, Let's just do the quiz. It's short, but the next problem I'm going to do is a little longer anyway. So, anybody have any more questions before I stop?